Thank you very much. Um, yeah, my name's Tim Panzak, and I've been at CRTech for the last 25 years. And there we developed RadCAD and Thermal Desktop with support from Marshall. And previous to that, I worked at Lockheed, where I developed TSS with support from Johnson. And my colleague, Mark Welch, has taken over the lead for Thermal Desktop, and it's given me some time to look at some other things such as this. So I do want to thank all the TFAWS folks for putting this on. It's still disappointing not to be able to be in person, but this is always a lot of work and a lot of things go unrecognized and behind the scenes activities to pull this off. So much appreciated for everybody involved in making this happen. It's not easy. Okay, so let's get started. We'll talk briefly about the motivation. That should be pretty self-evident. We'll spend a little bit of time on the architecture just to give a mental framework of how the process works, and really only doing that to help understand how you might use it yourself in a simulation. And we'll do a more detailed example that kind of showcases a variety of features and different approaches to modeling, really justifying why we're doing this. And then hopefully we'll have some time to discuss what we're currently working on. This is really kind of the prize, a 1D to 3D flow coupling in addition to the conjugate heat transfer activities. We've always wanted to do this. This has one of been Brent's goals for a long time, especially coupling the 1D and 3D fluid. We don't have a fluid flow solver, and we're not going to be in the business of writing one ourselves. So this is really satisfied a bullet that we've been trying to do for a long time. We've been working with ANSYS for the past couple of years, and it's actually been a lot of fun. I've worked on big projects before, and we've got stuff done, but it has always not been very fun. But this has been really good. We do have some other ideas where we can cooperate, and I'm just speaking for CRTech at this point, but they are just ideas. But things are going good, and we hope to continue this activity. Now, as far as applications, this audience would probably be better to tell me what the applications are than me telling you. But certainly a variety of places wherever there's fluid flow and heat transfer simultaneously with issues on both sides. So let's just talk about how this works. We're using ANSYS system coupling, which is a product. It's a program that actually has two parts. It has the user interface that the engineer directs the activities with, and then they also provide an application programming interface that third-party developers like ourselves can also hook into system coupling and join the party with all the other ANSYS simulation products. We're going to talk about Fluent, but it'll also work with CFX, and most people don't know this, but Thermal Desktop can also do nodal displacements remotely, so we could actually do a coupled mechanical system as well. So the way it works is you'll provide an input script to system coupling. There is a new GUI available that just came out, and I'm not too familiar with it, otherwise I'd show it to you. But that runs the process. System coupling will take it from there and launch Fluent. It'll launch CRTech products and get them to talk to each other. Now, I don't know if you've noticed, but there's blue here, and there's fluid here, there's yellow here, and yellow here. This is co-solving, so too bad this logo is already taken to make a good one for this thing. So, okay, so let's zoom in on this product here. You're probably saying, well, hey, Tim, I know how to run Thermal Desktop. I know how to launch a case. I know how to launch a Cinda. How in the heck is it going to talk to system coupling? Well, thank you for asking. So what we did was create a new executable that combines the ANSYS library, which lets us talk with system coupling, with OpenTD. And we've packaged up some OpenTD activities, some things into a sort of an easy to use object called CoSolver. This will be available in 6.2 for other developers as well. Well, what this does is when system coupling launches, when you run system coupling, it will launch our participant. The ANSYS term for players in the coupling in the co-simulation are participants. So to launch our participant, and via the input data that you put to system coupling, it'll pass along what it needs to connect back to system coupling, as well as the drawing, the thermal desktop drawing, and the case you want to run. So then OpenTD will launch thermal desktop if it's not running, and it'll run the case. And then we'll talk about how this works. If you have a domain setup that describes the interface, then an interface mesh will automatically be created. And I see from the icon we're still using punch cards, so maybe we'll upgrade that for the next version. But this data goes to the CoSolver back to system coupling. Now, the same type of information is also coming from Fluent. It's getting the meshes that are involved in the interface, and then ANSYS system coupling will make a map. It'll create the mapping between the Fluent nodes and the thermal desktop nodes to transfer heat flux, temperatures, whatever needs to be passed. Okay. In addition, what CoSolver does, it also creates a pipe. It creates a special communication pipe that is waiting when Cinda finally connects. When Cinda launches, it will connect with this pipe, and I'll show you how to make that happen. It's just a single line you put in your operations block. And that causes Cinda to connect with our coupler, and now it gets commands and data back and forth. So then during the simulation time, every iteration during a steady state, or every time step, every coupling time step, they don't have to be lockstep time steps. You can specify an interval, and each solver can run by itself till the synchronization point. Then data will be exchanged. So that's sort of just an overview of the architecture. The features in system coupling are pretty robust. So either participant can be steady or transient, any combination of either one, depending on the time scales involved. And at the interface between the fluid and the solid model, you can do different schemes. And I'll talk more about this later, because we ran into some interesting situations here with stability and performance. One way is usually the fluid supplies the flux data and the solid model supplies the temperature data. Neumann Dirichlet condition. If that doesn't work, a lot of times you'll see a convection coefficient and a reference fluid temperature, either free stream temperature or Y plus temperature, to describe the connection to the fluid side, and then the solid provides T again. Now, there's been some new advances in how to couple things using quasi-Newton methods, and this just came out recently with system coupling, and we've used it successfully. And we'll talk more about this later. And then there's other options too. If you have maybe some severe initial conditions that if you just let them go right at the beginning, it'll cause some craziness. You can slowly ramp up, let things ease into each other. And then one of another useful things is you don't have to have the models exactly aligned. If different coordinate systems were used, different conventions, you can map them to each other. You can provide a coordinate transformation to move one model into the other to line up the interface meshes. And there's a lot of good post-processing and debug tools. Of course, it runs distributed. You can do restarts, where say you do 10 iterations in steady state, take a look at the results. Not good enough. You can run 10 more and pick up where you left off. And system coupling can run either with a graphical interface, which I don't have too much experience with yet, or a command line. All right. So now I just want to go over what it would be like for the user to create an analysis situation. So it's not too hard. You'll create a working directory, put both the fluid and the thermal models in there. You'll create your input file to system coupling, which will tell it where these models are and and what the interface, how you want to match the interfaces up, and the names that you use when you match the interface up. You'll put all the elements that you want to be coupled to the fluid in a domain called coupling region. It's just something simple right now. It's just if you use the name coupling region for the domain, that automatically tells Thermal Desktop that you're planning on connecting to a fluid model, and Thermal Desktop will do what it needs to do to make that happen. Likewise, in Fluent, you'll set the zones. In Fluent, you can name the zones however you like. You'll select those zones and say for the thermal boundary condition you use via system coupling. So that gives the names that you use to connect in the system coupling file. And then to get CINDA to communicate and do a few other things, you'll add a single call in your operations block. And after that, you just run it and away it goes. So let's take a closer look at that. So you can set up your working directories however you like. This is just sort of a recommended way. Create a top level directory and put your thermal model, put your fluid model in that same directory. These are some, this run.bat launches when I just have this set up the way I like it. You double click on this, it automatically runs system coupling and tells it to read this input file, which is a Python input script. This is an example that we're going to have as a tutorial. So you can use this as a template if you like and just change the names of Thermal Desktop drawing in your case. In most cases, it'll be pretty applicable. Inside this, I won't go into detail on the actual syntax, but inside the script that gets sent to system coupling, you'll tell it where the executable is. You'll tell it what drawing you want to run, which case you want to run, and so on like that. Okay, so you set that up. Then in Thermal Desktop, you'll create a domain called coupling region. Here it's the outer part of this heating coil. And that automatically tells Thermal Desktop that this is going to be participating in a co-simulation. And it will create an additional network behind the scenes that goes to CINDA. Every node in the coupling region will have a conductor and a boundary node. That boundary node can be used for a variety of reasons, but typically it's used to represent the fluid temperature, and the conductor will be the convective coefficient. Likewise, in Fluent, you'll edit the zone you want, go to the thermal tab, and select via system coupling, and that's it. You'll set your Fluent model, you'll say, if you want to do a steady state, of course, you'll have to say, doing a steady state, or if you're doing a transient, you'll put in the transient parameters and things like that. But once the Fluent model is set up the way you want, all you do is say, this is the system coupling. When the thermal model's the way you want to set up, you just make sure those interfaces elements are in the coupling region domain. Okay, now CINDA, you put a single call to cosolve. And what this does, it sets up a lot of things in motion behind the scenes. It will search for the communication pipe that was created by our participant and connect to it. And then it'll communicate with it at key points. At the very beginning when you call cosolve, at the very end when CINDA shuts down, at the beginning of a steady iteration, at the end of steady iteration. Likewise, transients, if you're running a transient, beginning of the transient, every time step, the end of the transient, give you a chance to do whatever you need to do there. Now, it also does something clever here too. When you're in a cosolve mode, when you call steady, it actually puts steady in a loop. So you'll do steady state iterations over and over. You'll say, okay, call cosolve. You'll get the initial fluxes from Fluent. You'll do a run. You've converged all the way. You send those temperatures back to system coupling. Fluent does its job, sends you a new set of fluxes. So steady will stay in that loop and do steady states over and over until system coupling says, okay, both sides are converged, and then it'll send a message to CINDA to shut down. All right, so you set up your directories, you've tagged the surfaces that are participating at the interface, you put the cosolve in CINDA, and then you just run it. And system coupling will launch all the processes, and then there's ways of graphically showing the convergence as it's progressing too, but normally get a printout, it'll show you the progress and the changes in the convergence values of whatever you're exchanging across the interface. This example here, this was an ANSYS tutorial that we co-opted just so as a test case because we had answers from ANSYS, but this is going to be one of our tutorials. So this is already set up and it's kind of a follow along getting started process. So this converges in 3 iterations. And all right, so in addition to normal post-processing temperatures and such, you can also post-process some of the data that was created at the interface. So if you were coupling with a convection coefficient reference temperature method, you can post-process the convection coefficients and the fluid flow temperatures. Might help you understand the physics, or something doesn't look right, might help you debug the model. All right, that's kind of an overview of the user process.
Tim, there's a couple of questions.
Sure.
First one is, how does the coupling application communicate with ANSYS? Is that done with the ANSYS API?
Yes, system coupling is the ANSYS product. Okay, so system coupling knows how to communicate with Fluent. You would use, if you were not using any CRTech products, you would use ANSYS system coupling and do a fluid structure interaction program using all ANSYS products. So it has a user interface. It's already set up to communicate with Fluent. What they also do is provide an API so people like us can also bring our program to the party. So we communicate with ANSYS system coupling. ANSYS system coupling also communicates with Fluent. So it's saying it's getting temperature data from Cinda, passing it to Fluent, telling Fluent, okay, it's your turn, do a time step, do an iteration. Fluent then returns the fluxes, the system coupling, which passes it along to our participant, which passes it along back to Cinda, tells it to go, and that goes back and forth. So we're not communicating directly with Fluent. We're communicating strictly through ANSYS system coupling. And it's really nice because it keeps it a black box. We don't know anything about the mesh density on Fluent, and we don't care. So we're just saying, here's the interface, give us flux, and we'll give you temperature. Very nice.
All right. Another question is this coupling based on a domain decomposition or domain overlap approach?
Well, I'm not sure I understand the question, but the domains overlap. You don't have to have a conformal mesh. So the mesh on the thermal side can be different than the mesh on the fluid side, but the the physical locations of the mesh should be congruent. They should overlap. I mean, not overlap, but be in the same spot. Now there's mapping. There's all kinds of mapping controls for tolerances and things, just like we have in Thermal Desktop. All the things you can do when trying to get temperatures to the stress model, and they don't quite line up. But obviously, the closer you can have the geometry, better off you'll be to begin with. And we'll show you some stuff on there on some debug tools to show you that. So it works better if everything is in one interface for various reasons. So that's why for the thermal side, we put everything in one coupling region domain, and then that can map to one or more Fluent zones. So if that didn't answer, please send me an email, and if I can't answer it, I'll put you in touch with the experts that can.
And that's it for now.
Okay, thank you. Okay, so we did this model for starters, and we thought, yeah, that's great. Let's do something more complicated. And it was really kind of hard to figure out a good model to showcase. It's really hard getting permission to use anybody else's hardware for proprietary or sensitive nature of things. Easy, safe answer from lawyers is always no. And we thought, well, we could develop our own model. Let's do our own hypersonic airplane. Well, that either run the risk of doing something really bad and embarrass yourself, or if maybe we get lucky, we do something really good, we'd probably want to keep it a secret ourselves. So that wasn't a good idea. So we came up with this. It's a fun model, but it is a proxy for a lot of things being done in the aerospace, and it shows a lot of different things. It shows internal convection, shows how it interfaces with thermal desktop. We're also using radiation. Radiation actually turns out to be pretty important in this problem. I have a lot of one-dimensional flow-CAD refrigeration cycles. Brent did an interesting CO2 transcritical refrigeration cycle. We did some drain events, including CO2 dissolution and evolution. And it kind of shows, detailed modeling where detailed modeling is important, and system level modeling where that's appropriate. So anyway, so let's get on with that. We use SpaceClaim as sort of a common geometry input to both Fluent and Thermal Desktop, and that works out very well. So we constructed a model of this refrigerator with a keg in it. Here's the evaporator cold plate. It does have a door on it. I just turned it off. And we use the SpaceClaim features for volume extraction to generate the solid that would go to Fluent. Fluent then meshes this. And we're also using FlowCAD compartments. And I don't know if you're familiar with that, but it's worth looking into if you're not. There's sort of almost a zero-dimensional fluid modeling scheme. We use a mesh purely for geometric reasons in order to locate a liquid vapor plane based on the volume, the fill level of the tank, and the gravity vector and stuff like that. But it creates a lump inside, a twin lump with a vapor phase and a liquid phase that computes what's going on in the stuff. So if you're not worried about convection currents and stuff in there, you can just use a single state to represent the volume. So we kind of wanted to show all things, all the different modeling things together. All right, here's the meshes. Fluent meshes that interior volume, and you can kind of see the rolled handle part here, and you can see the boundary layer elements. And then here is the thermal desktop model. And we use TD Direct to do this meshing, and you can see the meshes aren't conformal. They don't give me different resolutions, different types of elements. And the system coupling takes care of that mapping back and forth. There's some good debug tools. There's a tool called ANSYS from ANSYS that will post-process data produced by system coupling. Back in when I showed you that folders, I forgot to mention that system coupling will create a folder called SYC, and in there is restart data as well as other results, the log files and such. And one of the things you can post-process is the element mapping. And I was getting some strange answers, and it's because I had tried to be clever and tried to make this door, put a hinge on this door so I could open and close it. I thought it might be door opening event. Might be fun to analyze, but I had misaligned it, and I wasn't getting the mapping on the front of the door, and this kind of showed it instantaneously, and it was very easy to find and fix that. Okay, all right. So we got the model built and all well and done, but then we found out that this was a rather difficult model, which I guess was fortunate because it kind of forced us to look at a lot of things, and it was a good learning experience. So natural convection in itself is a very strongly coupled system. The flow influences the temperature influences the flow. As you put more energy in the system, you can develop a different pattern, 2 roll cells instead of 1, so it doesn't always converge nice and asymptotically. We'll come back to this topic here about stability, but the Biot number is a ratio of heat transfer by convection by the fluid side, not necessarily by convection, but just in this case, from the fluid, heat transfer into the fluid divided by the heat transfer in the solid. And if it's greater than 1, the flux temperature method isn't stable. So you have to use a convection coefficient and a reference temperature, a fluid reference temperature, and that tends to be stable. It can still be unstable in certain conditions, but it is much more robust, but it's also very slow. And then there's the IQN method, and we use this with very good results. So we'll talk about that. This is, it's similar to, regular Newton's method where you have a function and you're trying to find the roots. So you'll compute the derivative at a certain point, extrapolate that down to the x-axis to get a new y value and repeat the process until you converge to a 0. What this is, we're really looking at the round trip. So Fluent supplies flux, that goes to Cinda, Cinda supplies temperatures, that goes to Fluent, Fluent supplies flux. So we want convergence. We want the Q from one iteration minus the Q from the last iteration to go to 0. So that sort of becomes our working functions. But you can't, there's no way to numerically evaluate the derivatives because it's a black box on either side of the interface. So what the quasi part refers to is it looks at the iterates. It looks at the data coming out of each iteration, and from that constructs the Jacobian. Actually, you can directly construct the inverse of the Jacobian using a variety of methods. Least squares is what's being employed here. So it's really clever. It's really new. Joris de Groot, I think, is one of the champions of the method if you want to Google it. Okay, so let's look what happened. So the first approach we used was the standard flux temperature coupling. Fluent supplies flux, Cinda supplies temperatures, and immediately went unstable. This is first iteration, second iteration, third iteration, fourth iteration. And I don't know what we're going to do. Let's take a look at why this is unstable. Here's a simplified view of the problem. What we have is a solid model over here. This orange line kind of represents the interface. We have a wall temperature that's part of the solid thermal model. We have a wall temperature that's part of the fluid model. Our convergence, we want this to be the same. For this simple example, we'll say the fluid model is connected to some sink fluid temperature at 0. The solid model is connected to some sink temperature at 1. Process starts with solid model temperatures being transferred to Fluent. Fluent does its solution step and computes the flux from the wall into the wall or out of the wall. In this case, it's going to start with 1, okay, and we'll get a flux of 1 watt. Now suppose this was, supposing that was 1 watt per degree, this was 2 watts per degree, then we take the 1 watt here, we pull it out here, and now we get a delta T at 2, minus 2, so that goes to minus 1, gives us a flux of positive 1. With that flux positive 1, this goes up to 3, which gives us 2 watts into there, which gives us minus 5, and so on. You can go through the process and see that it's not stable unless this effective fluid conductor is less than the effective solid conductor. Now, in cases where this is true, you can always reverse it. Sometimes this is a large cell size and a very low conductivity. It's a small cell size and a high conductivity fluid, mercury on insulation. You could go the other way around and have the fluid program provide temperature and the solid provide Q. But we really couldn't do that in this case because it's really more interesting. These are changing with the program, and the actual stability analysis is much more complicated. Goodenough, normal mode eigenvalues and all this kind of stuff. But it turned out this this problem was kind of right on the cusp, so we couldn't use a QT and we really couldn't do the reverse of a TQ either. So we tried the convective coefficient reference temperature method, and this is sort of the most common method of doing this kind of coupled problem. And in here, instead of getting the flux that the fluid program computes, the fluid program will convert that into some free stream temperature or Y plus temperature. There's a variety of schemes for figuring out what a good fluid temperature would be, and a convection coefficient. And that physically makes sense. It's nice, but you can see how this kind of anchors the wall temperature. If we just put a Q in here and we say, okay, Cinda, go ahead and solve, the wall temperature can vary quite a bit, but here it's kind of constrained. As the wall temperature deviates from the reference temperature, the heat will go in and out one way or the other to try to kind of stabilize it. So this tends to be very stable. And if you go through the same process, what we're really looking at is how the temperature changes, dt dq going into the wall. And for the fluid, we're looking at dq dt, the inverse of that. So it's really dt dq times dq dt, and that has to be less than 1. If you kind of go through that process, you'll get something look like this, and you can see that this is always less than 1. Okay, so we did that. Let's wire it up for that and try it. Yeah, it worked. It worked, but it's really slow. And you can see even after 120 iterations, it's not quite converged. Maybe out here it'd be converged. 60 more, I don't know. So ANSYS had just come out with this quasi-Newton method, so we took a look at that and we tried it, and look at that. And so it's very stable. It stabilizes the QT method that would normally be unstable, and it's also very, very quick. Now, this is just out of the box standard default settings for the method. We're working with the ANSYS folks to see if we get the most optimum, and if there's best practices we can recommend to people. There's also a little extra secret sauce in here. I'm not quite ready to tell you the recipe, but we've been working with the ANSYS folks, and if it turns out to be a good idea, we'll let you know. If it turns out a bad idea, it never happened. Okay. Here's some thermal results. And again, the purpose of this model wasn't just say anything profound about Kegerator design. It was just to demonstrate that this coupling will work on a variety of conditions, including ones that tend to be very adverse for doing a coupled model co-simulation. But we can see the effect of the door seal here. You can see the convection coefficients. This is the exterior of the cabinet. The temperature range is not very much here. This is the back side where you might stuff the compressor motor and thermostats and stuff like that. Close up of the door seal. Now the keg itself is the fluid inside the keg is modeled with a compartment. Okay, and the compartment consists of, again, that's a lump. That's a twin lump. It has 2 phases. And then the compartment itself is an flow-cat object, and it will compute for you. It'll compute all the proper ties to the wetted part, all the proper ties to the dry part, and that's dynamic, as you can have ports connected to here, pumps and filling and whatever modeling techniques you want to use to make this volume go up and down, and the compartment recomputes what all those ties are automatically. We also have an earn node, an equivalent radiation node in here, and the compartment takes care of that, connecting up all the dry areas with this equivalent node. In this case, not very interesting. We only have 1 lump here, and it's all the same temperature. But you can turn different selection rings on to have access to it. There's some post-processing features that are kind of neat. This is transparent keg showing you the liquid level here. Okay. Here's a pseudo transient. Okay, we did a number of cases, so all the results here aren't for the same case. There's kind of a mismatch of all kinds of results. But here's a pseudo transient cool down, and you can sort of see how the convection cells bobble around. We're not quite converged. I didn't run this to convergence. You can still see the skirt and the top rim here getting a little colder as things go by. But you can tell that it's working reasonable. Okay. Here's some Fluent results. Lots of things you can post-process in Fluent. I should have made the kegs actually in there. It's kind of transparent. I made it too transparent. You can kind of see the rim here, and it's 2 cross sections showing the temperature of the fluid. This blue part is where the cold plate, the evaporator, sticks through those post-processing planes, and you can kind of see the air trapped underneath the bottom skirt here. It doesn't circulate. It doesn't get up to the cold plate, so it stays a little warmer. Here's a velocity plot showing the magnitude of the velocity. You can map all kinds of things on here. It's very, very powerful. Here's some path lines, kind of useful to get an idea of what's going on, where the roll cells are, and what the principal modes are for losing heat and gaining heat. And you can also animate this here. I'll show you an animation here. This is showing the fluid flow. You see it sort of dropping down off the cold plate, embracing the keg, rising up, giving the heat to the evaporator. It's neat. You can look at the flow. You can see it kind of go through the handle here. And I think this hole in this handle actually affects it. It's a little stronger heat transfer down on this side. I think it's because of the downdraft that actually goes through this handle here. But again, this wasn't this wasn't to model a keg and show anything great about a keg. Although if I were mining ice on the moon in some skylight cave, I might appreciate a beer after the shift was over. So who knows? Okay, so that's it for the conjugate heat transfer part, the thermal fluid coupling. We can take any questions here, Doug, if you have any, and then we'll go on to 1D to 3D flow coupling that we're currently working on.
I'm not seeing any new questions.
Okay. Okay. So this is what we're currently working on, and it's to combine the one-dimensional FlowCAD with the three-dimensional Fluent or CFX flow modeling. And they're very complementary solution strategies. They really work well together. Of course, FlowCAD is fast, perfect for system level modeling. Fluent is detailed, it captures the physics, but it's expensive. If you had a situation where you weren't capturing the physics with a 1D model, you may not be able to do it with a full 3D model. It might be just entirely intractable. Of course, if you're missing something and that needs 3D, the 1D isn't going to do it. So these two methods work well together. You use each method where appropriate. So the 1D, they actually the same fluid system. It's the same fluid being exchanged between the 1D and the 3D networks. So again, this audience probably knows a lot more about this than I do, but what we're envisioning is, there's a lot of cases where a response surface just doesn't work. And this is normally the case like in Fluent. We'll have our Fluent, we'll have a fan and it's described by some pressure curves. And if we didn't have measured data, maybe you're designing something, you use a 3D model, 3D flow model, CFD model, and get flow rates as a function of pressure, valve position, and things like that. And now you have this tabular version of your complicated system that you drop in your 1D model. But it may not be appropriate for some strange things, like you can have something strange in your control system that you didn't account for, and maybe shocks and water hammers going down, and it makes the valves unstable. You may be required to model these events in a co-simulation. So this is kind of where we want to apply it. Also where it's difficult to characterize the process in terms of a table, maybe a tank filling and draining. So Fluent can solve the detailed process of filling and draining inside the tank. FlowCAD handles the supply and return lines and all the other control valves, and Thermal Desktop does the heat transfer part. Or maybe crew comfort, combined 1D, 3D environmental control system that's being driven by environmental heating from orbital, from solar and planetary heating and such, and maybe even combines a human body model. Stay tuned on this one too. We've got some interesting stuff going on there too. So this is what we're currently working on. ANSYS has devoted the resources, and we're very happy to see that they're enthusiastic about this. They've committed a gentleman in the UK to develop UDFs, which is user-defined functions. This is Fluent's version of user logic to extend it. It's very powerful. But they're connecting it to system coupling for us, so we don't even have to deal with this. It's just there'll be a new interface in system coupling where instead of exchanging temperature and heat flux, we can exchange mass flow and get pressure back. So it's very clean, very, very clean. We are developing new graphical objects in FlowCAD that'll be in Thermal Desktop. So you can say, I want to create a Fluent inlet and connect your FlowCAD model there, or I want a Fluent outlet with an E, and we'll connect the FlowCAD model to that. And what's important too is like for the thermal interface, you want the objects to be in the same place. And if they're not in the same place, you can still, they have to be in the same place with a coordinate transformation. But in the power of the 1D FlowCAD modeling is you can have a schematic view of things. It's abstract. You wouldn't want to make a scale model of a entire petrochemical plant. So we'll preserve that kind of feature too. So um, you don't have to have the fluent connection, the inlet, represented exactly in physical space where it really is. You'll be able to tell it where it is and put it where you like in your abstract schematic kind of layout. Given what we learned with the stability with the Keg model, we took some time to make sure our coupling approach was stable and worked. So we did quite a bit of testing and scheming on how to get FlowCAD data and Fluent data to talk to each other. And basically, it's very simple. It's a upstream gives mass, flow rate, and temperature, and the downstream supplies pressure. Okay. Now, well, you got a 1D and a 3D. How do you match them up? Well, the interface is going to be 2D. So the FlowCAD has just a scalar for the flow rate, pressure, and temperature. What Brent did was actually generate a profile generator. So given the Reynolds number and Nusselt number and such, we'll reconstruct what a fully developed profile looks like. And this is what will go to system coupling, and system coupling will then transfer this to the Fluent inlet condition. Say this is the inlet condition. So we're going FlowCAD scalars expanded into a 2D mesh. And likewise, Fluent's going to give us, say, the pressure, the back pressure map. We'll integrate that to get a total pressure and so on. So this was some interesting stuff. And this kind of avoids, if we just did a flat front into the 3D FlowCAD model, you might have some very strange, numerical instabilities as well as maybe wrong answers or maybe taking longer than it should. You might have, the other way would be to make a fake inlet, or extend the inlet a little bit to make get it fully developed profile before it dumps into the, your device that you're trying to model. So this kind of avoids that. And likewise, this is the work that the ANSYS folks did. We create this. So Cinda is going to send temperature and flow rate data to our coupling program, our participant. The participant's going to expand that into a 2D flow profile. That 2D flow profile is going to go to system coupling, and it's going to go to Fluent. Fluent's going to return a pressure map, which we'll integrate, send that result back to FlowCAD. And likewise for the other way, do the reverse for the inlet and the outlet. And we've tested this out with dual processes. It's 2 separate FlowCAD models running in 2 separate processes, 2 separate Fluent models running in 2 separate processes, and now we're ready to wire them up. Each of us, the ANSYS guy is going to take one of our FlowCAD models and replace his part, and I'm going to do likewise, take one of our FlowCAD models and replace it with one of his Fluent models. So I'm going to get to that as soon as I'm done with this presentation. Yeah, some acknowledgments are appropriate. Mike Rowan is the manager of the partner program. He's been enthusiastic and been a good champion for us inside of ANSYS, has supplied us with the resources that we need, both in terms of their software and in terms of putting us in touch with the right technical people. And one of those being Oleg Chernunkin, who is the lead developer for system coupling. We've worked closely with him. And just recently, Adam Anderson has joined us, and he's been doing the Fluent part here. So we're looking forward to getting that finished up and being able to say some interesting things about that. So that is about it. Quick summary. We'll have this available in 6.2, the heat transfer part, the conjugate heat transfer part. It's easy to use if you already know Fluent Thermal Desktop. I wouldn't recommend jumping in cold without having some Thermal Desktop and Fluent training. But if, assuming you are familiar enough with Thermal Desktop and Fluent, or are working with somebody that's, you have a team, each of which is proficient with these tools, the system coupling is not hard to learn. It's well documented. We'll have template examples that you can cut and paste for most cases, but even so, it's still worth looking into the documentation that ANSYS provides. And there's some tutorials to follow that as well. We think we've advanced the state of the art a little bit with our coupling algorithms. Much better performance, much better stability than what's currently out there. And it's going to be a built-in feature on our end. We're not going to license this as a separate feature or anything like that. 1D to 3D fluid coupling is proceeding well. It's really too early to commit to 6.2, but an outside possibility. If not ready for 6.2, then shortly afterwards, either as a 6.2 patch or 6.3 beta. And if you can't wait until then, give us a call. We'd be happy to set you up with a beta version or discuss anything, any particular applications. Now's a good time to throw in some requirements if you think you have something special or interesting. Love to hear about it. And hopefully we'll have an in-person hands-on lab for next year. Hopefully they'll have the fluid flow in there as well. And so that is it. So if there's any more questions, I'll be happy to answer them.